estimate the total duration of a project based on a critical path duration variance. We'll use Monte Carlo simulation. So what's Monte Carlo simulation? Monte Carlo simulation is um, a multi-probability simulation. It's a mathematical technique which is used to estimate possible outcomes of an uncertain event. How does Monte Carlo simulation work? This is a methodology or method used to predict a set of outcome based on estimated range of values versus a set of fixed input values. All these would be clear in the example. So in other words, we are using probability distribution to randomly sample an certain event and calculate what will be the outcome or the result of this randomly selected event on the outcome. The outcome of this myth or this example would be the project duration. Monte Carlo simulation usually is repeated thousands of times in order to get an accurate result. Our example today will be very simple train of events or activities ranging from A to J, and it's kind of like in a line, so like it's back-to-back activities. Each this table shows the activity duration in the optimistic level and the most likely level and pessimistic level. All these 10 activities. So based on the optimistic estimation of duration of the these 10 activities, the project will end in 23 days, but in the most likely would be 31 days, and pessimistic would be 40 days. The exercise today is to use Monte Carlo simulation to get the most probable total duration of this 10 activities or this project. We'll use Excel today in order to estimate, use like very basic functionality of Monte Carlo simulation. So we listed all the activities from A to J and the optimistic estimation of the duration of each of these activity. The most likely duration and also the pessimistic duration. So the total based on the optimistic, as we mentioned before, 23 days, and based on the most likely is 31 days, and based on the pessimistic would be 40 days. But Monte Carlo simulation, we will randomly, first of all, we have to assume the distribution of the uncertainty here. So we have we'll take A as an example. It's optimistically would be 2 days, pessimistically would be 6 days. We will assume the distribution between the 2 and 6 would be uniform, just to make it easy for us. Other distribution would be normal, would be logarithmic, would be exponential, would be like we have so many distributions, but like for the simplicity of this example, we'll use uniform distribution. So before we go into the Monte Carlo simulation, we'll estimate based on PERT. PERT is kind of using the distribution that it's really it's skewed to the most likely estimate. So basically, would be the pessimistic plus 4 multiplied by the most likely plus the pessimistic, and this would be divided by 6. So now PERT will estimate all these for these activities, and the total will be 31 0.16. Of course, like we'll just round it to 32 days. In this table, we will um, sample the duration based on a uniform distribution between the optimistic and pessimistic estimation of the duration of each of the activities. We'll use this 500 times. We will sample this 500 times, as we can see here. So basically what we used is random between the optimistic and pessimistic, and we just pick a number here. This will be done 500 times, and for B 500 times, C 500 times, and then we will do the total of this duration 500 times. Now we have to see what will be the probability of ending this project, and we need to draw the histogram of this duration. So in order to do this, we go to data and data analysis, histogram, and for the histogram we will the range will be the duration, and just to make it easy, I just like I ran it one time before, and the range and the bin would be easier if we use uniform distributed bins, and we will use we'll get this in a new sheet. Well, okay. Oh, it seems like we are duplicating the range. Now we have only one range here, and this would be the duration. Just make sure that we are going through this correctly, and okay. And we get new sheet here. It's still calculating. Now it should finish. Yep, we have it here. Sorry, my computer is because we are recording video, so it's taking a lot of the resources. Now we have starting from 23 days up to 40 days. This is the frequency of each of these durations. We'll just calculate the cumulative frequency here. Because of this 500 times, so this would be 0. This would be equal to this divided by 500, and we have to multiply this by 100 to get. And now we'll use this plus this the frequency, how many times this 26 days came up in the 500 multiplied by 100, and yes. Or we'll just do this here. Okay, so the probability that we end in 24 days is 0. The probability we will end in 25 days is 1.6%. The probability we end in 26 days is 1% plus 1.6%, which is 2.6%. In 27 days is 1.8%, but we already passed the 26, which is 1 and 1.6, and the total would be like 4.4%. So this would be the accumulative percentage. So this would be the probability and percentage. Sorry, this should be percentage. So this will be a cumulative probability, and it's usually we are taking the 95% confidence that the project will end in this number of days. So we'll just get this histogram here. So if we keep adding up the probability of each of the days, like 24 days, 25 days, 26 days, we end up in 95%. We are confident that the project will end in 35 days. So based on this simulation, we are estimating that the project will take only 35 days to get to the end of its life. So comparing this with the optimistic, so now we'll just write down 35 days here. So optimistically, we'll do this in 23 days. Most likely will be 31 days, but 95% probability that we will do this in 35 days. PERT estimate this in 32 days. So we have these numbers, and I'll just go with the MonteCarlo simulation. So MonteCarlo simulation can be more complicated than this. So these are simple events. We have just like a uniform distribution of 10. Imagine like you have a project that it has 250 events. And these 250 events, all of them are not in the critical path. We have maybe um, like the critical mass would be like 50 of these 250, but with some uncertainty, we might have the critical mass sway to another path that what we are expecting. That's why Excel will be like very bottleneck in this process. So I reproduce this calculations in R. R is a statistical language that is developed for all these for the statistical analysis. So these are the libraries I'm using. And now I did a function, like I just developed a function to estimate the total, each of the event duration based on uniform distribution. So this is our uniform distribution, and getting this in one data set and then calculating the total and then getting the quantile, 95%, the 95% probability that this project would be done. So I did this 100 times and run, it gives me 35 days. 500 times run, give me like 36 days. If we do this 1,000 times, 35 days. If we do this 5,000 times, this would be 35 days. So more, with more iterations, I'm more confident that the project will be done in 35 days. And this is 10,000 times. So if we do this in Excel, I'm telling you that this will be like a nightmare. So this is 50,000 times. So every time I'm getting the same result, this gives me the confidence that the project will be done in 35 days based on the data I'm feeding this model with. Of course, in real life, the project will be more complicated than this, but this is a simple example that I use in order to get this straightened and make it very easy to digest and understand.